Hi there, my name's Steve Maddox, Product Development Manager at Teledyne E2V in Chelmsford. Here at Teledyne E2V, we're well known for our cutting-edge imaging capabilities in CCD, CMOS and infrared sensors for space missions. But in recent years, we've also been working on new novel sensing capabilities for space in the area of quantum technology. These groundbreaking new sensors harness the quantum properties of atoms to turn the atoms themselves into extremely sensitive sensors that can be used for measuring inertial effects, accelerations, rotations, measuring gravity, as well as measuring magnetic fields and timing. This new platform technology is emerging from the lab and has seen successful scientific demonstrations on sounding rockets and the International Space Station. We've previously developed the CASPA CubeSat, which demonstrates all the technology building blocks to prepare a cold atom sample within a 6U form factor. We've been working on a follow-on Pathfinder mission and a payload that would use cold atom technology for the first time to deliver real Earth observation atmospheric data. The thermosphere is the region from about 90 to 1,000 kilometers altitude. It's a highly variable region driven by solar and geomagnetic activity, as well as by gravity waves generated in the lower layers of the atmosphere. Below about 600 kilometers, atmospheric drag is the dominant orbit perturbation and represents the largest source of uncertainty for orbit predictions. With the rapidly growing number of satellites in that region, conjunctions occur more frequently, and accurate orbit predictions gain importance for collision risk assessment, with consequences for satellite operation and service provision. To improve orbit predictions, new observations of thermosphere density are clearly needed, in particular in the region 300 to 400 kilometers during medium and high solar activity. Such density observations can be most accurately derived from acceleration measurements, provided that they're supplemented with measurements of atmospheric winds, temperature and composition. The combination of these measurements offers the unique opportunity to not only provide a new dataset covering a very poorly observed region, but will also allow to verify gas surface interaction models. These can then be retroactively applied to existing datasets from missions of opportunity, creating value far beyond the CASPA-ADM mission. The satellite concept is based on a 16U CubeSat carrying a cold atom interferometer accelerometer as the main payload, and supplemented with a mass spectrometer and a RAM wind sensor. Deployable solar panels are required to satisfy the power demand of the cold atom interferometer accelerometer. To achieve a complete local time sampling within a limited lifetime of a CubeSat flying at an altitude of initially 400 kilometers, an inclination of 40 to 76 degrees is needed for fast local time progression. All of this is compatible with a launch from the International Space Station. In order to take a measurement using a cold atom interferometer, the atoms go through a number of stages. First, the atoms are released into a vacuum chamber and captured in a cloud and cooled using a combination of lasers and magnetic fields. There's no use of any cryogenics. The atoms are used to form a matter wave interferometer, which is sensitive to the very small accelerations felt by the satellite as it passes through areas of different density. With our partners, University of Birmingham and RailSpace, we're currently building a breadboard of the payload, which will include an engineering model of the physics package. This will be optimized and tested to validate the numbers used in our previous models and studies. We're currently looking for routes to fund the remaining development of the mission, the payload and the satellite, and then the launch and operations. So to summarize, although this mission will fulfill a critical science case and deliver valuable data in its own right, we see this as a Pathfinder mission at the beginning of a long, exciting roadmap for this technology. This mission will play a critical role in the validation of the technology in orbit, raising the TRL and proving the concept. We can see routes to miniaturize the technology further in the future and to increase the performance by adding additional levels of cooling. Sticking with this mission concept, we could imagine a number of these satellites operating in a constellation to form an operational service that provides real-time observations of atmospheric density, which could be used as input to space weather models and orbital predictions. Once validated, the same technology has many additional applications in gravity sensing, station keeping, and navigation, for example. Thanks for listening. Please get in touch if you're interested in finding out more. We'd love to hear from you. Thanks.